Hello, I'm doing problem number 11 from chapter 12, and it involves a ladder that's leaning against a wall that has a weight of 500 newtons and a firefighter that's on top that has a weight of 800 newtons. So I drew the free body diagram with the friction holding the ladder in, and this is a ladder and it's against a wall. The force of the ground, or the normal force, going up, the force of the wall going outwards, and the weights of the ladder and the firefighter. So the problem says that this is at equilibrium. So because it says it rests against a friction wall, so it's at static equilibrium. So the sum of all forces and the sum of all torques equals 0. So here's our sum of all forces expressions. So we have the force of the wall and the force of friction in the x direction, and then the weights of the firefighter and ladder in the y, with the force of the ground also in the y. And then our torques, we're going to be taking it, since it wants us to start from the ground, and that's just the easiest point, we're going to start down there. Then so we have, here are our different forces. So we have the force of the wall, and that's 15 meters away, and the angle between the radius and the force is 60 degrees. Then right here we have a radius, since it's midway, it's going to be 7.5 meters, 500 newtons down because that's the weight of the ladder, and then 30 degrees in between. And then next we have the force of the firefighter, and that has a 30-degree angle between the radius and that force. Then these other two forces, the force of friction and the force of the ground, have a radius of 0, so that we're not going to include them into our sum of all torques expression. So there it is. The force of the wall times the radius times sine 60, because remember alternate interior angles, that's 60 degrees. Then the ladder, which is midway, 15 divided by 2 meters, and sine 30 because it's 30 degrees in between. And then for the firefighter, he's 4 meters away. Okay, so then if we solve for the force of the wall, we get 267.51 newtons. And earlier here we saw that the force of the wall is equal to the force of friction. So I just put that there just for reference. Then for the second part, we're going to be getting the force of the ground, and that's a lot easier. So here, if we go back to our forces in the y direction, we have the force of the ground is equal to the weight of the ladder and the weight of the firefighter, and both of those are givens. So we already find the weight of the force of the ground. So now for part 2, I redrew the new free body diagram, and the firefighter is now up at 9 meters up, and it's about to start slipping. So first we should be dealing with the torques, because the radius of the firefighter has changed. So I did the sum of all the net torque expression, and the only thing that's different now is that the firefighter is 9 meters instead of 4 meters. And then also I didn't forces in the x direction expression, because we're going to be dealing with weight, the force of the wall and the force of friction. Okay, so we're gonna be solving for the force of the wall, because that will help us get the force of friction, which we're solving for, and then it'll help us later on get to the normal force. So if we solve for the force of weight, which is going to be the same thing that we solved for earlier, except 9 meters instead of 4 meters there, we get the force of the wall, and then the force of the wall is equal to the friction, which is 421.47 newtons. Then we know that friction is equal to the mu, which is the coefficient of friction, times the normal force, and in this case the normal force is the force of the ground. So that way we can solve for mu static, which is 0.32. Thank you.